Okay, now let's look at another example of using fixed second law. It's the mass transfer from the surface of a sphere into an infinite quiescent medium. So you have a sphere, and the sphere has radius r. There are particles like hold the particle concentration on the surface of the sphere, and it is maintained at a concentration CAS. And then you have a medium which is infinitely large surrounding this sphere. And then we assume these are quiescent. Quiescent medium. And at the same time, we assume the concentration in the quiescent medium is Ca infinite. The infinite means the medium is infinitely large, and this concentration refers to the concentration at the far away from the sphere. But it just means it's a background concentration before um before diffusion happens. Or you can just understood it as something at infinite. Okay, that's the problem. So we are going to study this for consider as a steady state situation. For a steady state situation, and well, let's first look at the fixed segment. So it tells us the partial C partial T equals to the AB Laplacian CA. Now under steady state, it means time independent. Time independent means any time derivative is non-exist. So if the fixed second law tells us that the whole term equal to 0, then it tells us Laplacian equal to 0. Now, due to the spherical symmetry and the radial diffusion, we would express the equation in spherical coordinates with angular symmetry. So we consider diffusion flux which is only radially coming out. There is no direction which is rely on any angle. So we have flux along the r direction. So in this case, it's spherical symmetry. The Laplacian gives us 1 over r squared dr r squared dca r equal to 0. So this is our governing equation for this problem. And we have boundary condition. So whenever you write down a governing equation for your problem, the first thing you want to do is specify its boundary condition. So the boundary condition, we need two boundary conditions because it's a second order derivative. The boundary condition one is, you can see on the surface at I equal to R, the concentration of the solute in the medium at I equal to capital R is the same as the concentration on the surface. Second boundary condition is as R approaches to infinite, the concentration goes to CA infinite. Okay, now let's solve this equation. So let me write it down. This is our equation. So since it's r squared, like you can multiply both sides by r squared, it will not give you anything different. So you know this guy equal to 2. If this equal to 0, that means, well, something, a derivative with respect to r, or the primary, or the independent variable give you 0, the derivative is 0, that means the function itself is a constant, C1. Then you can say, okay, dCA dr equal to C1 divided by r squared. Then you can integrate it again, so you get a general solution, which is CA as a function of r is minus C1 divided by r plus C2. C1 and C2 are constant of integration and to be determined by boundary conditions. So let's see. We use BC2, boundary condition 2. You will get minus C1 divided by infinite, which is basically 0. 0 plus C2 equals to CA infinite. It gives you C2 equals to CA infinite. So now you can write out your profile as minus C1R plus CA infinite. And then you use boundary condition 1. It means minus C1 divided by R plus CA infinite go to CAS. It tells you C1 equals to R multiplied by CA infinite minus CAS. Okay, now you plug the C1 and the C2 into the expression, we get our solution. CA as a factor of R. It's equals to CA infinite minus CA infinite minus CAS multiplied by capital R divided by little r. Okay, we solved it. This is the concentration profile of this problem. Once you have concentration profile, you can do a lot of things. For example, you can figure out what's the radial flux. NAX equals to minus DAB. DCA divide DCADR. Well, what is DCADR? It is minus DAB. DCADR, you just take derivative with respect to the concentration. It give you CA infinite minus CAS multiplied by capital R divided by R squared. Now, if you wanted to know the solute flux at the surface, solute. You are asking what's, so it's not NAX, it's NAR. So what is NAR evaluated at I equal to capital R? It will be minus DAB CA infinite minus CAS divided by capital R. Or you can change the sign, it's DAB divided by R multiplied by CAS minus CA infinite. Okay, now let's see what does it mean. If CAS is larger than CA infinite, that would usually be the case, because if you have something like you have a pill or anything or sugar you dissolve in water, then the concentration of the sugar on the cylindrical, or sorry, on the spherical candy would be higher than the concentration in the water. So you would have CAS larger than CA infinite. And in that case, you would get a NAR is positive. That means you have outward flux. So it will make sense. Otherwise, you would have, if CAS is less than C infinite, that means the concentration in the bulk is actually larger than the concentration on the surface of the sphere. Then you would have diffusion inwards, like into the sphere. Now you can also compare the flux expression. I'll compare the flux expression as transfer coefficient. Means NAR at R equal to Km multiplied by CAS minus CA infinite. And if you compare this equation, you would easily see, okay, now for this problem, Km equals to EAB divided by R. Now, if you recall what we did in the last lecture, for diffusion from an infinite plate to a stagnant semi-infinite medium, we had a totally different Km. So in that case, the Km was dependent on time. And in this case, the Km is a constant, it's independent of time. So you can see the mass transfer coefficient depend on each scenario, and it's case dependent. So that's why I emphasized the last time, you needed to know which physical problem you are dealing with, and then which Km, the Km in this is also one of our example for spherical diffusion problem. Like, does the example we covered in the lecture cover your scenario? If yes, you can use the equation corresponding to that example. If not, then you cannot use the Km we derived here. So this Km is a very nice looking simple form. This is for this particular problem, which is spherical surface diffused into an infinite stagnant medium. Okay, now let's also think about the Sherwood number. How about the Sherwood number? The Sherwood number is, if you recall from last time, it was defined by KML divided by KAB. Recall KL is characteristic length of the problem. Now in our problem, the characteristic length is the diameter of the sphere, which is 2r divided by DAB. So you substitute the Km. Km is just discussed as DAB divided by R. multiplied by 2R divided by 2AB equal to 2. Okay, for this problem, the Schroeder number is 2. And it turns out to be a very elegant, simple number. But again, it's case dependent. So this is a Schroeder number for stagnant medium. Or for quiescent medium, it's the same thing. Means there is no fluid flow. You may ask, okay, if there is a flow, so if I'm considering the case of I have a diffusion problem, I have a radius r, and I have an incoming flow. But the flow is coming from a uniform velocity v infinite. And then I still have diffusion. In this case, you can see that it's totally a different scenario, and the stagnant scenario we just derived, like Sherwood number equal to 2, no longer applies. And for this case, it's like if you want to solve it analytically, it's extremely challenging. So usually people develop empirical expressions or from experiments. Now here we are going to introduce, just write down the result from an empirical result. This is true. I have a bullet point. True with the number with a free stream velocity. Be infinite. So in this case, our modified Sherwood number would be 2.0, which was the number comes from the previous derivation, plus a correction term. The correction term reads as this. Reynolds number to the power of 1/2, 0.6 multiplied by Reynolds number power to the 1/2, and the Schmidt number power to the 1/3. So the Reynolds number, you have heard about it. This will be the raw density of the medium, the infinite velocity of the medium, and the 2R, this is the diameter of the sphere, divided by the dynamic viscosity of the medium. Now this SC, we show me the number to defined by the dynamic viscosity of the medium divided by the density of the medium multiplied by AB. It's the same as the kinematic viscosity of the medium divided by the diffusion coefficient of the medium. So this is called SC is number. Now, again, whenever you have a non-dimensional group, this is another group of dimensionless group. Dimensionless group. Whenever you have a dimensionless group, look at the numerator, look at the denominator, and figure out what's the physical significance of this Schrödinger number. So the numerator is the kinematic diffusion coefficients. So it means the momentum diffusion of fluid. Denominator is the mass diffusion of the solid. So this dimensionless number compare the relative significance of these two factors. Since I'm already right here, let me also write down the Reynolds number in case you would like to have a review. Reynolds number. It is a ratio of inertial force to viscous force. So every non-dimensional number tells you something. Okay, let me also review the Sherwood number we discussed the last time. We see the convective transport to transport. So the requirement is that for you and especially it's a necessary skill if you go to like industry, being engineer or anything. Like the training for the reason we have these type of classes and this type of discussion, the training is you understand why there are dimensional groups ever exist. And then whenever you see a new dimensionless group that you have never seen before, how do you interpret its meaning by looking at the expression? So that will be something good for you to math. Let me see. That's all I would like to cover about the spherical scenario. So just a few comments. So when you have a free stream velocity V infinite, this show the number would increase. So if you have a higher Reynolds number, you have a higher Sherwood number. If you have a higher Schmidt number, you have a higher Sherwood number. Intuitively, what's the reason? So if you have increased velocity V infinite, well, if V infinite is 0, then the Sherwood number would reduce to just 2.0. Now with V infinite, the incoming free stream velocity increase, then you increase your Reynolds number, and as a result, you increase your Sherwood number. That means with the increased velocity, the Sherwood number, which is a ratio of convective transport versus diffusive transport. Now the convective transport become more and more important as your incoming flow velocity increases. That totally makes sense. Okay. Now let's look at an example. A small spherical catalyst particle of radius given is submerged in a stagnant liquid containing a solid at the bulk concentration. Okay, it tells you what's the bulk concentration. The solid concentration at the surface is maintained at 0 due to instantaneous reaction. Interesting. Okay, this is a case that the concentration on the surface of the sphere is 0, but it is actually larger on the bulk part. Interesting. The diffusion coefficient of the solute in the liquid is given. Calculate the steady state mass transfer coefficient and the flux of a solute into the particle surface. Okay, let's draw the diagram here. Let's see the particle. Wow, should not draw any dots because there's no concentration on it. So on the particle, let's leave this up. And the particle C and C here. And the infinite C infinite, you have 0.02 mole per meter cube. Okay, let's see. Calculate the steady state mass transfer coefficient. So for this problem, we just discussed that the mass transfer coefficient is DAB divided by R. And this equation applies to this problem because it satisfies the condition that the medium is infinitely large and the medium is stagnant. And we have a spherically symmetric sphere, so we can use this equation. It will directly give us little km. So and the radius. Okay. It also asks us to find the flux. Okay, find the flux. Equal to km CAS. Km multiplied by CAS minus CA infinite. Okay, let's see. What is Km? 2 times 10 to the minus 7 meter per second. CA is 0 minus A infinite 0.02 mole per meter cube. Okay, to give us an active number. Negative 4 times 10 to the power of minus 9 mole per meter second, so per meter squared second. What does it mean? It means solute diffuses towards the sphere. So then since 0, it means it's evaluated by equal into the sphere. And leave you guys one exercise.